Generally, it is not acceptable to have multiple main disconnects for a single distribution system. The National Electrical Code requires that every service, feeder, or branch circuit shall have only one main disconnecting means. Having two main disconnects can indeed lead to confusion, especially during maintenance or emergencies. This redundancy may cause uncertainty about which disconnect to operate in case of a fault or emergency, increased risk of leaving one disconnect in the on position while the other is off, creating an electrical hazard, and difficulty in verifying that the system is completely isolated for maintenance or repairs. While it is understandable to provide convenient access for maintenance personnel, it can be achieved without compromising safety. Alternative solutions should be considered. Firstly, install a walkway or access panel to allow maintenance personnel to safely reach the new disconnect without encountering obstructions. Secondly, provide clear signage and instructions to direct personnel to the new disconnect location. Thirdly, establish a policy that maintenance work should only be performed with the new disconnect open. Based on the principles of safety and adherence to electrical codes, it is recommended to eliminate the redundant main disconnect, install the main disconnect in the designated location, provide safe and accessible pedestrian pathways for maintenance personnel, and establish clear operating procedures and training for maintenance staff. By adhering to these guidelines, the design will enhance safety, minimize confusion, and ensure compliance with electrical regulations. The National Electrical Code, or NEC, is a comprehensive set of standards and guidelines for electrical wiring and equipment installation in the United States. Its purpose is to ensure electrical safety and protect people and property from electrical hazards. The NEC is updated every 3 years by the National Fire Protection Association, or NFPA, to reflect the latest advancements in electrical technology and safety practices. It is widely adopted by state and local jurisdictions as the basis for their electrical codes. The NEC covers a wide range of topics related to electrical installations, including wiring methods, overcurrent protection, grounding, equipment installation, and special occupancies. It provides detailed requirements for the selection and installation of electrical equipment to ensure that it is suitable for its intended use and that it is installed in a safe and reliable manner. One of the key principles of the NEC is that electrical installations must be designed and installed to minimize the risk of electrical shock, fire, and other hazards. This is achieved through a combination of prescriptive requirements and performance-based standards. Prescriptive requirements specify exactly how certain electrical components must be installed, while performance-based standards allow for alternative methods of installation as long as they meet certain safety criteria. Overcurrent protection is another important aspect of the NEC. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical circuits from excessive current flow, which can cause overheating and fire. The NEC specifies the types and sizes of overcurrent protection devices that must be used in different types of electrical circuits. Grounding is also a critical safety measure that is addressed in the NEC. Grounding provides a low impedance path for fault current to flow back to the source, which helps to trip over current protection devices and prevent electrical shock. The NEC specifies the requirements for grounding electrodes, grounding conductors, and bonding of metallic equipment. The NEC also includes requirements for special occupancies such as hazardous locations, healthcare facilities, and swimming pools. These occupancies have unique electrical safety requirements due to the presence of flammable materials, sensitive medical equipment, or conductive environments. Compliance with the NEC is essential for ensuring electrical safety and preventing electrical hazards. Electrical inspectors use the NEC as the basis for their inspections, and they have the authority to require that electrical installations be brought into compliance with the code. Failure to comply with the NEC can result in fines, penalties, and even legal action. The NEC is a complex and comprehensive document, and it is important for electrical professionals to stay up to date on the latest changes and revisions. The NFPA offers a variety of training and educational resources to help electrical professionals understand and comply with the NEC. In addition to the NEC, there are other electrical codes and standards that may be applicable to certain electrical installations. These include state and local electrical codes, as well as standards developed by organizations such as the Institute of Electrical and Electronics Engineers, or IEE, and Underwriters Laboratories, or AL. It is important to be familiar with all of the applicable codes and standards before designing or installing any electrical equipment. Electrical safety is a shared responsibility, and everyone has a role to play in preventing electrical hazards. By following the NEC and other applicable codes and standards, we can help to ensure that electrical installations are safe and reliable. In the context of electrical disconnects, the NEC provides specific guidance on the number, location, and type of disconnects required for different types of electrical systems. The purpose of these requirements is to ensure that electrical equipment can be safely de-energized for maintenance, repair, or in the event of an emergency. The NEC generally requires that each service, feeder, and branch circuit have a readily accessible disconnecting means. A service is the electrical supply from the utility company to a building or other structure. A feeder is a circuit that carries power from the service to a distribution panel or other load center. A branch circuit is a circuit that supplies power to individual electrical loads, such as lighting fixtures, receptacles, and appliances. The disconnecting means must be capable of disconnecting all ungrounded conductors of the circuit. Ungrounded conductors are the conductors that carry current to the load, typically the hot or phase conductors. The disconnecting means must be located at a readily accessible location, meaning that it must be easily accessible without requiring the use of tools or equipment. The disconnecting means must be clearly marked to indicate the circuit that it controls. The disconnecting means must be suitable for the intended use, meaning that it must be rated for the voltage and current of the circuit that it controls. The NEC also includes specific requirements for disconnecting means for certain types of equipment, such as motors, air conditioners, and electric heaters. These requirements are designed to ensure that the equipment can be safely de-energized for maintenance or repair. In this situation described, the proposal to relocate the distribution cabinets with their own main disconnect switch, while leaving the existing disconnect switch in place as a convenience for maintenance personnel, raises concerns about compliance with the NEC. As stated earlier, the NEC generally requires that each service, feeder, or branch circuit have only one disconnecting means. Having two main disconnects for the same distribution system could be considered a violation of this requirement. Additionally, the redundancy of having two main disconnects could create confusion and increase the risk of electrical hazards. Maintenance personnel may be uncertain about which disconnect to operate in case of a fault or emergency. There is also a risk of leaving one disconnect in the on position while the other is off, creating an electrical hazard. To address these concerns, it is recommended to eliminate the redundant main disconnect and install the main disconnect in the designated location. If convenient access for maintenance personnel is a concern, alternative solutions should be considered, such as installing a walkway or access panel to allow maintenance personnel to safely reach the new disconnect without encountering obstructions. Clear signage and instructions should be provided to direct personnel to the new disconnect location. A policy should be established that maintenance work should only be performed with the new disconnect open. By following these recommendations, the design will enhance safety, minimize confusion, and ensure compliance with electrical regulations. Let's delve deeper into the specific sections of the National Electrical Code that address disconnecting means. While the NEC is a comprehensive document, certain articles and sections provide the most relevant guidance for this scenario. Article 225 covers outside branch circuits and feeders. Section 225.31 specifically addresses disconnecting means, stating that means shall be provided for disconnecting all ungrounded conductors that supply or pass through the building or structure. This reinforces the requirement for a single, readily accessible disconnect. Article 230 pertains to services, which are the conductors and the equipment that deliver electricity from the utility to the building. Section 230.70 requires the service disconnecting means to be installed at a readily accessible location either outside of a building or structure or inside nearest the point of entrance of the service conductors. This further emphasizes the importance of a single, easily accessible disconnect for the entire electrical service. Article 408 deals with switchboards, switchgear, and panel boards. While it doesn't directly address multiple disconnects in the same way as the other articles, it does emphasize the need for clear identification and accessibility of all overcurrent protective devices and disconnecting means within these assemblies. This indirectly supports the principle of avoiding redundancy and potential confusion. Let's consider some practical examples to illustrate the potential problems with having multiple main disconnects. Imagine a scenario where an electrician is called to troubleshoot a power outage in a building. They arrive on site and find two main disconnects, both labeled similarly. Without clear and unambiguous signage, they might inadvertently disconnect the wrong one, potentially shutting down critical systems or creating additional problems. In another scenario, during an emergency situation such as a fire, firefighters need to quickly de-energize the building's electrical system. If they encounter multiple main disconnects, they might waste valuable time trying to determine which one to operate, potentially delaying their efforts to extinguish the fire and rescue occupants. Consider the implications for electrical inspections. If an inspector finds multiple main disconnects for the same distribution system, they would likely cite the installation as a violation of the NEC, requiring corrective action to be taken. This could involve significant expense and disruption to the building's operations. Furthermore, the presence of multiple main disconnects could create confusion regarding responsibility for maintenance and repairs. Who is responsible for ensuring that both disconnects are properly maintained and functioning correctly? What happens if one disconnect fails? These are just a few examples of the potential problems that can arise from having multiple main disconnects for the same distribution system. The key takeaway is that redundancy in this area can create confusion, increase the risk of electrical hazards, and potentially violate the NEC. Now, let's explore some alternative solutions for providing convenient access for maintenance personnel without compromising safety or code compliance. One option is to install a remote-operated disconnect switch. This type of switch can be located in a readily accessible area, while the actual disconnect mechanism is located closer to the distribution cabinets. The remote-operated switch can be controlled from a distance, allowing maintenance personnel to de-energize the system without having to navigate obstructions or travel long distances. Another option is to install a transfer switch. A transfer switch allows for the transfer of power from one source to another, such as from the utility grid to a generator. Transfer switches can be designed to provide a single point of disconnect for the entire electrical system, while also allowing for the connection of a backup power source. Clear and unambiguous signage is essential for any electrical installation, but it is especially important when there are multiple disconnects or other potentially confusing elements. Signage should clearly identify the circuits that each disconnect controls, as well as any relevant safety information. In addition to signage, it is also important to provide training for maintenance personnel on the proper procedures for de-energizing and re-energizing electrical equipment. This training should cover the location and operation of all disconnects, as well as the potential hazards associated with working on electrical systems. Finally, it is important to establish a written policy that outlines the procedures for de-energizing and re-energizing electrical equipment. This policy should be readily available to all maintenance personnel and should be reviewed and updated regularly. By implementing these alternative solutions, it is possible to provide convenient access for maintenance personnel without compromising safety or code compliance. The key is to carefully consider the specific needs of the installation and to choose the solutions that best address those needs. Remember, electrical safety is paramount, and it is always better to err on the side of caution when designing and installing electrical systems. Now let's address the topic of lockout/tagout procedures in relation to electrical disconnects. Lockout/tagout, often abbreviated as LOTO, refers to safety procedures used to ensure that dangerous machines are properly shut off and not able to be started up again prior to the completion of maintenance or repair work. It requires that hazardous energy sources be isolated and rendered inoperative before any employee performs servicing or maintenance on machines or equipment where the unexpected energization or startup of the equipment or release of stored energy could cause injury. In the context of electrical disconnects, lockout/tagout procedures are essential for preventing accidental energization of equipment during maintenance or repair. The basic steps of a lockout/tagout procedure are as follows. Firstly, identify all energy sources that could potentially energize the equipment. This includes electrical, mechanical, hydraulic, pneumatic, and thermal energy sources. Secondly, notify all affected employees that the equipment will be shut down and locked out. Thirdly, shut down the equipment using the normal operating procedures. Fourthly, isolate the equipment from all energy sources. This may involve disconnecting electrical power, closing valves, or blocking moving parts. Fifthly, apply lockout devices to all energy isolating devices. Lockout devices are typically locks or tags that prevent the energy isolating devices from being operated. Sixthly, verify that the equipment is de-energized. This can be done by testing the equipment with a voltmeter or other appropriate testing device. Seventhly, perform the maintenance or repair work. Eighthly, remove the lockout devices and re-energize the equipment. This should only be done after verifying that all employees are clear of the equipment and that it is safe to do so. Lockout/tagout procedures should be documented in writing and should be readily available to all employees. Employees should be trained on the proper procedures for locking out and tagging out equipment. In the case of the redundant disconnects, the lockout/tagout procedure becomes more important. If one disconnect is left on while the other disconnect is off, it can cause confusion to other maintenance personnel who may see the disconnect in the off position and not perform proper verification on the equipment. Now let's consider the importance of arc flash hazard analysis. An arc flash is a dangerous electrical explosion that can occur when a fault in an electrical system creates a high-energy arc. Arc flashes can cause severe burns, blindness, and even death. An arc flash hazard analysis is a study that is conducted to determine the potential arc flash hazards in an electrical system. The analysis typically involves calculating the incident energy and arc flash boundary for various locations in the system. The incident energy is the amount of energy that a worker would be exposed to if an arc flash were to occur. The arc flash boundary is the distance from the arc flash source at which a worker would be exposed to a certain level of incident energy. The results of the arc flash hazard analysis are used to determine the appropriate personal protective equipment, or PPE, that workers must wear when working on or near energized electrical equipment. The PPE may include arc-rated clothing, gloves, face shields, and helmets. The results of the arc flash hazard analysis are also used to develop safe work practices for working on or near energized electrical equipment. These safe work practices may include de-energizing equipment before working on it, using insulated tools, and maintaining a safe distance from energized parts. In the context of multiple disconnects, an arc flash hazard analysis can help to determine the potential arc flash hazards associated with each disconnect. This information can be used to develop safe work practices for operating and maintaining the disconnects. For example, if the arc flash hazard analysis shows that there is a high risk of arc flash at one of the disconnects, workers may be required to wear arc-rated clothing when operating or maintaining the disconnect. The arc flash hazard analysis should be conducted by a qualified electrical engineer. The analysis should be updated regularly to reflect any changes to the electrical system. In addition to the arc flash hazard analysis, it is also important to implement an electrical safety program. An electrical safety program is a comprehensive set of policies, procedures, and training that are designed to protect workers from electrical hazards. The electrical safety program should include procedures for identifying and controlling electrical hazards, as well as procedures for responding to electrical emergencies. The electrical safety program should be reviewed and updated regularly to ensure that it is effective in protecting workers from electrical hazards. By implementing an arc flash hazard analysis and an electrical safety program, it is possible to significantly reduce the risk of electrical injuries and fatalities. When dealing with electrical systems, safety should always be the top priority. Finally, let's discuss the importance of regular maintenance and testing of electrical disconnects. Electrical disconnects are critical components of an electrical system, and they must be properly maintained and tested to ensure that they are functioning correctly. Regular maintenance of electrical disconnect should include the following steps. Firstly, visually inspect the disconnect for any signs of damage, such as cracks, corrosion, or loose connections. Secondly, clean the disconnect to remove any dirt, dust, or debris that could interfere with its operation. Thirdly, lubricate the moving parts of the disconnect to ensure that they operate smoothly. Fourthly, tighten any loose connections. Fifthly, test the disconnect to verify that it is functioning correctly. Testing of electrical disconnect should include the following tests. Firstly, insulation resistance test. This test measures the resistance of the insulation between the conductors and the ground. A low insulation resistance reading indicates that the insulation is damaged and could pose a shock hazard. Secondly, contact resistance test. This test measures the resistance of the contacts in the disconnect. A high contact resistance reading indicates that the contacts are corroded or damaged and could cause the disconnect to overheat. Thirdly, operational test. This test verifies that the disconnect operates smoothly and correctly. The operational test should include opening and closing the disconnect several times and observing its operation. The frequency of maintenance and testing of electrical disconnects will depend on the environment in which they are located and the frequency of their use. However, as a general rule, disconnects should be inspected at least annually and tested every 3 to 5 years. The results of maintenance and testing should be documented in writing. Any problems that are identified during maintenance and testing should be corrected immediately. By implementing a regular maintenance and testing program, it is possible to ensure that electrical disconnects are functioning correctly and are providing a safe and reliable means of disconnecting electrical power. When it comes to electrical systems, proper maintenance and testing are essential for ensuring safety and reliability. By following the recommendations outlined above, you can help to protect yourself and others from electrical hazards. In conclusion, while the initial intention behind retaining the existing disconnect might seem convenient, the potential for confusion, safety compromises, and code violations outweighs the perceived benefits. Adhering to the NEC guidelines, prioritizing a single, well-placed disconnect, and implementing robust safety protocols will ultimately create a safer and more reliable electrical system. Remember to always consult with qualified electrical professionals for any design or modification of electrical systems.